Hi everyone, this is our video on our flowcharts with regards to our correlation and regressions. So first off, I want to go back through our decision tree, which is listed in the beginning of the PowerPoint, right? So when do we choose correlations and regressions? Right, that's kind of the big question for all of the tests we run in this class is what requirements do we have to meet to run these tests? So the first thing that we're going to look at is what type of data is the dependent variable. And when we run a correlation and regression, the dependent variable should always have a parametric classification. In our class, this means it'll be ratio data. Okay, because we're not going to use any interval data examples. So we need a parametric dependent variable, aka a ratio classification of our dependent variable data. Then we have to look into what type of data our independent variable is representing. In correlations and regressions, both the dependent and the independent variable will be parametric data. Okay, so ratio data. In other words, you have quantity values that have been measured and not quantity values that represent categories. Okay, those types of independent variables would be when we use t-tests or ANOVAs. So in this case, both parametric or both ratio type data for both the dependent and the independent variable. Okay, we also have to meet a certain list of assumptions. Okay, so the first two are going to be assumptions for every single test we have in this class, right? And that's that we have a normal distribution because that allows us to compare our sample to our population, right? And then we also have to have random sampling, which is essentially going to help us get to a normal distribution, right? But kind of the concept that everybody in the subset of the population that we've chosen has an equal chance of being included in the sample. Okay. Number 3 is that we have linear relationships between variables. Okay, so curvilinear relationships will not be accepted in correlations and regressions, specifically if we're doing linear correlations and regressions, which we are only doing in this class. Okay, so you have to be able to calculate a linear relationship, which is indicated by Pearson's correlation coefficient R. And then we also need to have homoscedasticity. Okay, meaning if you think about heteroscedasticity, that's where we have the fanning effect, right, where residuals gradually become larger. Residuals being the difference between a certain pair of points on a coordinate system and their distance from the line of best fit. So if that distance or the residual is gradually increasing as we move along either the independent and or dependent axes, right, that creates this fanning effect known as heteroscedasticity. So we have to make sure that our residuals, or the average of the residuals, or the average of the distances from points to that line of best fit are relatively the same. Okay. Additionally, you could add a fifth assumption on the basis of what types of variables you're using. So if we want to add in like a pseudo fifth assumption that you have both parametric independent and dependent variable or variables, that is also acceptable. Okay, so I've included a blank version for you guys to fill out on your own, but this is to check, right? You can use this as a study tool to make sure you understand the certain pathways and the assumptions that you're supposed to meet for any given test. Okay, so going into our output for SPSS, this is kind of a guide that will help you read the output. Okay, so these portions in the blue clouds are going to represent different tables of interest to you within your output. So the first table usually you'll see in the output is going to be your descriptive statistics, so your mean and standard deviation if that's something that you chose. Okay, the correlation matrix is where we end up getting our bivariate correlations or bivariate comparisons between variables. Okay, so for this, right, we usually have those asterisks that I mentioned in the activity video that come up next to certain values in the table. And what these are going to represent are significant relationships, okay? And the default for SPSS is 95% level of confidence. So you're kind of just assuming any asterisks that pop up are in reference to that 95% level of confidence. In other words, we're using an alpha of 0.05, right? And this is considered 0.05 in both tails, since we're always going to be talking about two-tailed tests. Okay, so given a certain R value, right? Remember, for correlations, we're looking at relationships. So our null hypothesis for correlations is that there is no relationship, meaning R would be 0, right? Between any two given variables. So the null hypothesis that we're evaluating when we look at these asterisks, right, in our table is we're saying there is no relationship between any two given variables. If you see an asterisk next to a pair, right, a variable pair, that's going to indicate that P is less than 0.05, in which case we reject the null hypothesis, and we would accept the research hypothesis that says we do have a significant relationship between the two variables. If you do not see an asterisk, that's going to indicate that there's enough error, right, or there's a large enough probability that you don't have a significant relationship. In other words, P is greater than 0.05, so you would accept the null and say there's no significant relationship between variables, or there's just no relationship, right? So that's the first table you're going to come across that is of great importance to you. The next table you'll come across is the model summary. This is where we see what our R-squared values are, as well as how R-squared changes and how that's going to affect our selection process. So you'll see a p-value for change statistics. This will show up as sig for change statistics. And this is calculated using a statistic we haven't talked about yet, which is an F statistic or an F score. So don't worry about the parts of the table between your actual R-squared change and the significance of that change statistic. Okay, but basically what that sig column means, right, is that your null hypothesis for that given choice, right, is that if, depending on the method that you're using, right, the addition or removal of a given independent variable is not going to change R-squared significantly. Okay, so this is the hypothesis that we're testing when we look at how R-squared changes with the addition or removal of variables. So based on the addition or removal, right, if we end up with a p-value greater than 0.05 in that sig column, it's going to indicate that we're not changing, right, R-squared significantly. In other words, we accept this null hypothesis. However, if we see a p-value that is less than 0.05, right, that means we're going to reject the null in the sense that we're saying adding or removing a given variable significantly contributes to the prediction of the dependent variable. In other words, we have increased or decreased the R-squared value significantly enough that we have now identified the point or the value of the R-squared that is going to be most useful to us. Okay, so this is the model summary table, and usually we're going to go with the model number that provides us with the highest R-squared value, which more often than not is going to be the last model listed in the table. And this is, we have a good example of this in the activity video. For the coefficients table, this is the last table of interest. So there is a table in between model and coefficients. That's the ANOVA table. Don't worry about that. Just skip over it. And you'll look at the coefficients table. This table is what you will use to build your regression equations, whether you're looking at a bivariate regression or if you're looking at a multiple regression. Okay, you'll see the first column in your table usually represents the order of the variables that were listed in the model, and then alongside of those you'll see this unstandardized coefficient labeled B. Those are the values you're going to use to build your regression equation. Okay, so with that, the first one you usually see is B sub 0, which is going to be represented as constant. So this is your y-intercept. That is not going to change from equation to equation. Okay. After that, if you have a variable inserted into your or your independent variable inserted into your regression equation, there's going to be a value listed next to that variable, which is B sub 1. And then that's going to be paired with any given value of x for that variable. Okay, so in our body fat example in the activity, let's say that this first variable is thigh measurements. Okay, in which case we're saying thigh measurements are a predictor for body fat, which would be considered our dependent variable, or y. Okay, so given any measurement of a thigh skin fold, we could say we have this general relationship of an increase, right? Or increases relative between x and y, right? So then we put in whatever that given value of x is, and that tells us what the change in y would be as a result of that x value. Okay, so then we end up doing this for all of the variables that are listed in the model. So when you write out your equation, right, you're filling in the B coefficient parts. When you're actually using that equation to predict the dependent variable, that's when you add in values for x. But otherwise, your equation is just going to be whatever the B coefficient is times x for that given variable plus a B coefficient for another variable times x for that given variable, right? You're building an equation to use to predict y, or the dependent variable. Okay. Within this coefficients table, you'll notice there are p-values or a significance column for the coefficient b, and this is going to be represented by a t-statistic, okay, or the t-statistic, and then there's going to be a significance value next to that. So in this area, we're looking at how well does the value of b, or how well does the coefficient for a given independent variable contribute to the prediction of the dependent variable, right? Does it actually significantly add to the prediction equation? If it doesn't significantly add to the prediction equation, then we know it doesn't carry a lot of weight in the prediction of the dependent variable. So within this area, the significance column will give you a p-value either greater than whatever your level of confidence is, or it'll give you a p-value less than your given level of confidence, right? What we're looking for is a p-value less than your level of confidence, which again our default is 0.05. So p-values less than 0.05 tell us we reject the null hypothesis. In this case, the null is that the value of b does not significantly contribute to the prediction of the dependent variable, right? But like I said, if we include a given independent variable, we want that b coefficient to be significantly contributing to make sure that we've got a decent and accurate prediction of our dependent variable. So in this case, we want p less than 0.05, which would indicate that the relationship between the independent and dependent variables is significantly contributing to the prediction of the dependent variable, which means we would want to keep that b value included. Okay, so this is a general flowchart of how you're going to read the actual outputs that you get from SPSS for correlations. Correlations specifically, you'd only be looking at this part. If you're doing a linear regression, you're kind of considering all of this flowchart. Okay. Moving on, if we're looking at methods of forward selection and backward elimination, these ones I feel like people usually don't connect with right away because it is a little bit complex on how things are added or removed. So I've made this flowchart as more of a step-by-step kind of process on how how SPSS is programmed to select given variables. Okay, so remember the goal in forward selection is that we're trying to determine if the addition of a given independent variable is significantly increasing r squared. Okay, remember the ultimate goal of the regression is to get the largest r squared possible. Okay, so in forward selection, we start with no variables in the model. So I've added this one here, which isn't usually listed in SPSS. So you can think of this as model 0 in SPSS, right? But we have no variables in the equation. And then for each subsequent model, we're just going to add a variable one by one to see if the addition is going to increase r squared significantly. Okay, so in your models table in SPSS, right, kind of if we're going back to this one, right, we're looking further into this table here in the forward selection and backward elimination. Okay, so you can kind of reference back to that if it makes more sense to you. But that p-value for the r squared change, the null hypothesis for this p-value that's listed, or for that significance column, is going to tell us that r squared is not changing significantly. Okay, so if we add a variable and we notice that r squared does not change significantly, that means that variable is not really contributing much to our prediction equation. So in that case, we would say we don't need that variable added, so we'll just take it out. Okay. On the flip side, if p is less than 0.05, that's saying the change is significant, which means we have increased our r squared value significantly, thus we would want to keep that independent variable, because again, the goal is to get the highest r squared value possible. So if we use this evaluation method, right, in our model building, we say the first model, we start with nothing. That would just be the constant between our, or whatever the y-intercept is for our equation. Okay, from there, we pick the independent variable with the largest r, right, because the largest r, if we square that value, will give us the largest r squared. So we're starting with the value that contributes to r squared the most. Okay. So we'll call this x sub 1. Okay, so when we add the first r squared, obviously it's going to be significant because we're going from nothing to whatever the r squared is for x1. Okay, so we're automatically going to accept this first model. In that case, we say obviously it's going to be a significant addition from 0, so we're going to add it in. And then we end up building onto our equation, right? So starting with b sub 0, if we add x1, right, we're going to have some coefficient for that independent variable plus any given value for that independent variable, right? And then let's say, well, we have more variables to choose from. Okay, so we're going to add the next variable that increases r squared the most, which we're going to say is x2. Okay, let's say when we add this, the significance, right, or the p-value column for the r squared change is going to be less than 0.05. So this would mean we do have a significant change in r squared. So that means we would keep that variable in the equation, right? So then we end up with this version where we have our first variable, which significantly added to r squared, and our second variable, which significantly added to r squared. Okay. Next, let's say we have another variable to choose from, right? We're going to add the next variable that increases r squared the most, which we'll call x3. But let's say that when we evaluate the change in r squared, we get a p-value that's greater than 0.05, which means we're not significantly adding to r squared anymore. So that means that x3 doesn't really add a lot to our prediction of the dependent variable, which is what we're really interested in. Okay, so if it's not significantly contributing to r squared, we're just going to leave it out of the equation altogether, which is where we get this equation, right? We don't include x3. So that's why I put this in parentheses, because this last equation is not included in the SPSS output, right? So usually I say use the last row, right, or the last model in your output, because that's going to give you the equation with the highest R squared, right? This in SPSS, it's already removing this last model, saying like, well, we tried adding another variable, but it didn't significantly change R squared, therefore we're not going to list it, okay? So I think that's the big takeaway, is the equation or the model is going to give you the largest R squared value is what you want, either out of forward selection or backward elimination. But the process of forward selection is that you're adding, right, independent variables into the equation such that you're significantly increasing R squared. When you stop increasing R squared significantly, that's where you stop your forward selection process. Okay. On the flip side, if we're looking at backward elimination, we put all of the variables into the equation, which we see here, and then from there we're going to remove one independent variable at a time. As we remove an independent variable at a time, we're going to be decreasing R squared. So a similar process is going to happen where we're evaluating the change in R squared. We just want to make sure that the decrease is not significant, right? Because if the decrease is significant, that means we've changed R squared too much and we need to reevaluate our situation, right? So if we're looking at the significance value, or the significance column in our R squared change area of our model summary graph or table, if that p-value is greater than 0.05, right, that means when we removed a given value, it didn't really change the R squared value significantly, so we can probably keep that independent variable in and then continue removing variables. Okay, so this is kind of weeding out variables that aren't that important. Okay, so on the flip side, right, if we find a p-value that is less than 0.05, that's where we reject the null and we say, no, R squared is significantly changing, right? If the removal of a variable significantly changes R squared, in this case it's decreasing R squared, right, that's a bad thing. So that would indicate we need to put whatever that removed variable is back into our equation so that it stays nice and strong, okay? So when we look at this in a hypothetical situation, right, again, model 0 in SPSS, in this case I'm calling it model 1, we put all of the variables into the equation, okay? Obviously the change in R squared is going to be significant because we have all of the variables in, right? And we're not removing or adding anything from the equation yet. So let's say we start with 3 different variables, right, and we get this equation to start with. The process that we're going to use in backward elimination is removing the independent variable that decreases R squared the least, right? So it's just the opposite of a forward selection method. In this case, we're saying x3 decreases R squared the least. Okay, so then we evaluate what is that change in R squared when we take out x3 from the equation. And we notice there's a p-value greater than 0.05, okay, for the removal of x3. So we're saying x3 doesn't really significantly contribute to our prediction equation. So we're just going to leave it out, right? And then we end up with this equation without that x3 in there. So then we say, well, we've got 2 more variables to choose from, right, or to manipulate in this equation. So we're going to remove the R squared, or the independent variable, right, that decreases R squared the least again. Let's say that's independent variable number 2, or x2, right? So we take it out of the equation, and then we evaluate how does R squared change, right? In this case, though, let's say that the p is less than 0.05, right? So that's saying R squared changed significantly by removing variable 2. That's bad, right? Because we now have decreased R squared significantly. And remember, our goal in a regression is to keep R squared as high as possible, right? with the most significant variables. So if we're decreasing R squared a lot, that means that variable is probably contributing to the prediction of our dependent variable significantly. Therefore, we need to put it back into the equation. Right? So in this situation, we hypothetically took out x2, but then decided it changed the prediction equation too much, so we put it back in. Right? And then we end up seeing that model 2 and 3 have the same equation. So model 3 in a backward elimination method usually is not included, right? Or in this scenario, it's not included because SPSS was able to say, no. The removal of a given variable significantly changed R squared, so we're just going to stick with the previous model that we chose, or the previous model that was calculated. Okay? Again, reiterating that when we use these methods, we want the largest R squared possible, right? That means we have the largest covariance, or the largest coefficient of determination. In other words, the largest percentage of a dependent variable that we can calculate using a given number of independent variables. Okay, so hopefully these flowcharts help you guys. I do recommend filling them out on your own. I again put blanks for every single flowchart, so you should be able to print them and test yourself, or you can type in them in the computer and check back with the filled in versions to check your answers. But I know students in the last 2 semesters have used these and said that they really help them understand the concepts of how forward and backward elimination work, as well as how to read the outputs for SPSS when they're working through their activities. So I would highly recommend going through these for practice, and then also using the flowcharts that you've made, or the flowcharts that I've provided for you to figure out how to read your outputs if you get stuck or if verbal instructions aren't enough. Additionally, you guys have a stat summary. So I'll put a blank and a filled out one. They're already on Beachboard, but I think this, for organizational people, if you're not as visual with the flow of stuff, I think this is a good alternative for studying. So you can see the first 2 columns are for correlations and regressions. Okay. For this week, you don't need to know how to calculate any of your assumptions. We're just going to go into our test assuming that we have met all of our assumptions. Okay. But there is a given list of assumptions. You guys do need to memorize these for the exam. Okay. So we have normal distribution, random sampling, linear relationships, and then in the terms of correlations, we want to have homoscedasticity. In terms of regressions, we want to make sure there's no multicollinearity. Okay. For both correlations and regressions, we're going to have parametric dependent variables and independent variables. The main difference between correlations and regressions is that you're using a regression to predict a dependent variable, right? So regressions are when we build equations to predict a dependent variable. Correlations are just looking at current relationships between any 2 given variables, right? And correlations can either be in respect to bivariate or multiple. Regressions could also be bivariate or multiple, and those are determined by the number of independent variables that you have identified. Okay. As far as the p-value for the main effect, for a correlation, the main effect is the relationship, or whatever the significance is for the correlation coefficient R, which is telling us if there is a significant relationship between variables. So the null hypothesis you want to know for correlations, right, is there a significant relationship? Null hypothesis says no, right? When we look at our regression, again, the main goal of the regression is to build a good predictive equation, right? And what we're actually testing significance for is the identified relationship between dependent and independent variables as far as independent variables being predicting factors for a dependent variable, right? So we're actually going to be looking or evaluating, right, the coefficient b for a given independent variable, saying, is this relationship between the independent variable and the dependent variable significant enough to be able to predict the dependent variable? Null hypothesis would say that whatever the value for b is for a given independent variable is not significant enough to predict a dependent variable. Okay, so again, flowcharts as well as this table I think are super helpful in this next test. So I would highly recommend going through them. There's a blank version of this posted in Beachboard, so you can feel free to fill it out for practice. But I think practice is kind of the hit-home message in the coming sections for this class.